Hello, I'm Vitor Barrote. I'm a research fellow at Monash University. I work in the laser ablation ICP-MS lab of the Isotopia facility, and I recently finished my PhD at the John DeLater Center at Curtin University. And my PhD was entitled For the Evolution of Replacement Type VHMS ore systems in the Yilgarn Craton, Western Australia. And today I'm going to present a case study from the Nimbus Deposit where we've applied the methodology that we developed for this study. VHMS, which stands for Volcanic Hosted Massive Sulfide, are important sources of copper, zinc, lead, gold, silver, and they account for more than half of the global production of lead and zinc, for example, as well as significant amounts of other base metals and gold. These deposits, they are formed near or at the seafloor as the result of mixing between seawater, pore water, and circulating hydrothermal fluids, which are driven by magmatic heat. Now, the magmatic hydrothermal contribution of metals is not necessary in the development of VHMS deposits. However, it has been suggested by a number of studies. The most commonly studied process in the formation of VHMS systems is seafloor accumulation of sulfides from the discharge of metals from exhaling hydrothermal fluids. However, more recent studies have also described large-scale subseafloor replacement as a mechanism of mineralization in both modern and particularly ancient volcanic successions. Doyle and Allen, 2003, they recognized the importance of subseafloor replacement in massive sulfide system, and they coined the term replacement type VHMS systems for deposits in which the ore precipitates from syn-volcanic hydrothermal solutions within the pre-existing volcanic or sedimentary rocks. And in that case, the replacement of the host stratigraphy by the mineralized massive sulfides is synchronous with the formation of the host sequence. Replacement type VHMS are therefore characterized by the absence of exhalates, and in its place, the mechanism of mineralization is by replacing the host stratigraphy. So you commonly find these replacement features of replacement fronts in the host rock. It is important in this case because you don't have that stratigraphic marker of the metals which are being accumulated in the seafloor. It's important to establish the syn-volcanic timing of replacement, particularly when clear syn-sedimentary features are not present. The demonstration of the syn-volcanic timing of ore is important not only to reliably classify a deposit as replacement type VHMS, but also it's vital in understanding the process that drove mineralization as a process that was indeed linked with this volcanic activity, or was it something that happened at a later time in the history of this deposit and therefore linked to another type of mineralizing system, which is going to be fundamental in understanding the evolution of the deposit and looking for similar deposits as well. So this map on the left here shows the VHMS occurrences as well as base metal occurrences excluding nickel in the Yilgarn Craton from Hollis and others 2017. And it's easy to see that it has a much lower frequency of known volcanic hosted massive sulfide deposits when compared to similar provinces elsewhere in the world, such as the example here in the right, which is the Superior province in Canada, which has a large number of known VHMS deposits. While it is possible that we haven't found these deposits because they possibly don't exist due to the characteristics, the geological characteristics of the Yilgarn not being favorable to VHMS systems. However, there is significant evidence that current exploration techniques have just failed to successfully address many of the obstacles to ore discovery in the Yilgarn Craton. For example, paucity of outcrop, the deep overburden, and in that case, what we really need in order to discover these deposits is to develop exploration tools that are well equipped to find new occurrences as well as detailed known occurrences of these types of deposits. And that's exactly what I've attempted to do for my PhD and in this study that I'm presenting here. So basically, we've developed a multidisciplinary approach in order to constrain all of the processes which are involved in the history of this mineral deposit. So we use different isotopic and geochronological techniques to constrain magmatism / deposition, as well as ore formation, alteration, and also secondary processes that might have affected this deposit at a later time in its history. And with that, we can build a 4D framework for the VHMS system, which basically accounts for the 3D evolution of this deposit in time. And with that, we're able to better understand the timing of ore formation, as well as understand what is the possible source of metals and what are the conditions for the ore precipitation. And that will ultimately lead to the discovery of new deposits. The understanding of the multidisciplinary approach, as well as the benefits that it brings into the study of these types of deposits, will become more apparently, hopefully, as I get into the example. And the example that I'm presenting here today is a portion of what I studied in my PhD, which is the Nimbus Deposit. Now, these results are published in a paper in Precambrian Research that you can access, although some of it is part of a manuscript which was recently accepted in Mineralium Deposita, but will be available to the public soon. Unless you are watching this recording from the future, in which case it might already be available, so go and have a look at it. The Nimbus deposit is located in the Kalgoorlie terrain in the eastern goldfields, and this deposit comprises a series of steeply dipping zones of massive and semi-massive sulfide, which is hosted by coherent and autoclastic dacitic rocks mainly, although there is record of mineralization hosted by mafic sills, and those have been interpreted to be coeval to the dacite. Both dacitic and basaltic lithologies have a peperitic relationship with less common carbonaceous mudstones. And the time of the formation of the host rock was determined by Hollis and others in 2017. They dated the dacite to be approximately 2.7 billion years old. So although we have well-constrained age for the host sequence, constraining the relative timing of ore is challenging because the usual textural and stratigraphic relationships which would allow us to do that in a more conventional VHMS systems are not observed in this deposit. So one of the main questions that we have here at Nimbus is the timing of ore. Is it syn-volcanic, which would make this effectively a replacement type VHMS, or is it happening at a later time and it's related to other events in the evolution of in the evolution history of the Yilgarn Craton and that have affected this deposit? Since the host stratigraphy is already well constrained by uranium lead ages from Hollis and other 2017, Our first attempt was to try and date directly the mineralization. So we used rhenium osmium to attempt to date the massive pyrite, which is the first sulfide phase of the ore mineralogy. And although we did obtain reliable age for sulfide precipitation, we did not get enough resolution to distinguish between volcanism or alteration related ore, given the low precision of the method. So the next step, we attempted to constrain the alteration, the timing of the alteration, since VHMS systems have an extensive alteration profile and alteration related to this mineral activity. So we were expecting to get an age which was approximately similar to the volcanism if these two processes were related. However, what we got from dating cerussite-rich altered plagioclase with the argon-argon method was a much younger age at around 2.63 billion years. So that intensifies our doubt of, okay, so is this mineralization related to the volcanism at 2.7, or is it related to this 2.63 age record, whatever that might be? And not only we found the record of this 2.6763 event in the plagioclase, but we also found metamorphic monazites, which are syn-foliation within a polymitic conglomerate to the east of the mineralized rocks, and we found that the monazites gave similar ages to the plagioclase, meaning that this is actually a significant event that is happening at 2.63 billion years. So these are the two options that we have so far, which are given to us by the constraints to the volcanism, by the crystallization of the dacite, and by the alteration ages given by monazite and plagioclase. And basically we have two different events happening around 2.7 or 2.63. And if we were to determine that the mineralization is related to the 2.7 event, then this would probably be a syn-volcanic VHMS. However, if the mineralization is happening at a later time and is related to the 2.63 occurrence, then this would mean a post-diagenetic replacement of the stratigraphy. And because our rhenium osmium direct dating of the mineralization basically comprises this whole area here, that's when we really need to get multidisciplinary in order to obtain an answer. So we had a look at the sequence northeast to the mineralized rocks of the Nimbus deposit. And this sequence comprises, at the very top, a succession of bedded polymitic conglomerate. Hollis and others, 2017, suggested that this succession was hanging wall to the Nimbus deposit, and they based that in evidence for northeast younging throughout the deposit, as well as the occurrence of hydrothermally altered dacite clasts within the conglomerate, as well as the lack of mineralization observed in the polymic conglomerate succession. The picture of this succession being hanging wall became even more clear after recent studies, which looked in detail to the alteration assemblages in each of these rock types, and that is currently being prepared by Hollis and others for publication. And basically what they describe is that the degree of alteration in the rocks within this so-called hanging wall succession is much lesser when compared to the rest of the deposit, which is another argument for the fact that these are hanging wall. And then the results that I'll present in the next slide are also adding to this observation that this hanging wall succession is indeed overlaying the mineralized dacites and basalts of the Nimbus deposit. We dated the sedimentation of the polymitic conglomerate with the rhenium osmium, but this time we combined the measurements from nodular pyrites, which are sedimentary in nature, with the black shale matrix to obtain better precision in the isochrone. And we also measured the trace element content in the sedimentary pyrites within different positions in the drill hole, in the sample drill hole. And what we observed is the occurrence of an interval which is enriched in trace elements as well as metals that are related to the that are present in the mineralization at the Nimbus deposit, and we've interpreted that to correspond to an increase of metal content in seawater, which is generated from the mineral activity nearby. And this is an indirect evidence for the syn-volcanic timing of ore, the record of this increase of metals combined with an age which is very similar to the age of volcanism, and in fact is within error of that age, to indicate that this enrichment in metals recorded by the sedimentary rocks is being generated by mineral activity in the system. In addition to that, this technique has the potential to be developed into an exploration tool by tracking the discharge of hydrothermal ore fluids into seawater during periods of active mineralization. And then this increase of metals is recorded by nearby successions that contain black shale and pyrite. Because trace elements are concentrated in pyrite, fluctuations in this metal content are much well observed when compared to a regular quarter core assay, which is a common technique applied by the mineral industry. It's also important to notice at this point that so far the geochronological tools that we've tried to apply haven't been able to provide us with conclusive discrimination between syn-volcanic versus post-volcanic activity. However, that's where the multidisciplinary approach really becomes a valuable asset, because we used this observation of fluctuation in metal content within a sedimentary package to infer an indirect timing of ore. So it makes much more sense that this is happening while the system is active during volcanism. Also because if you remember that 2.63 event is being recorded by metamorphic syn-foliation monazites, which are indeed within this conglomerate. So this must have happened, at a later time when all of these changes were already recorded by the pyrite. And this next part of the study has a similar idea to what I've just said, because we weren't able to precisely date the mineralization. Then we had a look at another geochemical tool that might be able to help us with a relative timing of the ore that might answer our question. So what we did next is that we measured lead isotopes in galena, and we used a method that was developed by Rex Taylor in Southampton using a double spike, 207-204 spike, which he has described to be 10 times more precise than previous methods which corrected lead data by a correction factor. And the other interesting thing about this method is that the amount of galena required is very, very small because of how much lead there is in those galenas. So we measured lead from a very, very small piece of galena which we dissolved, or we just put a little drop of HBr into a thin section, and then that will dissolve the galena, which then we pick it back up with a pipette, and we measure the content of lead in that. So we measured lead in two different types of galenas. What we called ore galena, which is associated to the polymetallic ore phase, which is the main mineralization. And the second type of galena is the late galena. And these galenas occur in late quartz carbonate veins that cross-cut the mineralized dacite. The ore galenas show very homogeneous composition, forming what we call the ore cluster. And that cluster represents the lead isotope composition of the polymetallic ore fluid within the main mineralization phase. However, the late galenas show a much distinct behavior, distributing along some sort of mixing line away from this ore cluster. We modeled the evolution of the lead through time from the ore cluster, and we've identified that the late galenas are broadly distributed along this line, meaning that they have a significant component of that is just this lead evolved through time, and that the reason why they might not fall directly in that line is probably due to an older component. So the lead in the late galena derives from three sources: the ore cluster, some older lead probably in the host sediments, and then in situ evolution of the lead through time. And because we have geochronological records with the use of other methods of something significant happening here around 2.63, we can then infer that these galenas are being crystallized at this time, and we can then understand how much the lead, which is provided by this point in time, is contributing to the composition of the galena, how much of the ore lead is contributing, and we can't really model the contribution of the older component. So what is important to observe here is that we have definitely two times of galena formation, and although we can't really date the age of the galena solely from the lead system, we can correlate these moments with other geochronometer techniques that we have applied. So the ore cluster galena was formed at an older time, and that was followed by the formation of the late galena, which is associated to veins. And we can then link that to the two known significant events that we have recorded in our geochronometers. And with that, we can say that the ore galena was formed at the 2.7 event, while the late galena is likely formed at the 2.63 billion year event, which means that the massive sulfide mineralization is happening at the later time, which corresponds to the volcanism, and that is an indirect evidence of the syn-volcanic nature of this VHMS system. And in addition to that, because we can quantify how much lead is being contributed from each of the sources to the lead isotopic composition of the late galena, we can then measure the composition of these galenas, and potentially that will indicate us towards a more ore cluster lead composition, which will then lead us to regions proximal to high-grade mineralization. So we're fairly confident to say that the VHMS model fits the timing of ore formation. So as far as timing is concerned, we are very confident that it is a syn-volcanic deposit. And that's important because it opens up the 2.7 billion year Cambalda sequence as a potentially fertile sequence for deposits of this type, which was already proposed by Hollis and others in 2017 and is further reinforced by the study presented here. In addition to that, the lead composition of late galenas has potential to vector towards high-grade ore, and also the trace element record of sedimentary pyrite could track time of mineral activity in nearby successions, and that could also have a potential value for exploration. The most important thing is that the multidisciplinary approach that we took was vital in getting conclusive results, because if we just applied one or few geochronological techniques, we wouldn't be able to come up with a more complete story of this deposit, and we would just not resolve the question at hand. This multidisciplinary approach was also applied to the Teutonic Bore Camp with another publication that is also part of my PhD thesis. So this was recently published in Ore Geology Reviews. And what's important to note is that because these are different deposits, and you will have different questions within different types of deposits, the techniques which were applied differ significantly. However, the idea of just applying a multidisciplinary study where you try to constrain all the different elements which comprise the evolution of the deposit is basically the same. And with that, we're able to understand the 3D evolution of the deposit in time and improve our exploration techniques. So if you're interested in seeing another example and learning a little bit more of what this 4D methodology approach is, then please refer to this publication. If you have any questions, then you can find my my contact in this website, which is the page of the Isotopia Lab. You can also hit me up on the socials. So this is my Twitter page. I'd like to thank GSA for the opportunity to present these results, and especially to Paul for making it possible for me to record this presentation, given that the monthly seminars are no longer possible within this isolation time. If you like this presentation, please press the like button, and if you would like to receive notifications about more presentations uploaded to this channel, then you can just click on the subscribe. Thank you.